We have talked about describing function analysis. This approach is utilized to predict the existence of limit cycles in certain nonlinear systems. The approach is applicable to systems which are in this form or which can be brought into this particular block diagram form. Here are the steps which we follow. If the system is not in this particular form, we bring it into this form and then assume this x to be equal to a sine omega t. That is, we assume a sinusoidal solution for this particular system. Then we approximate this nonlinearity by a describing function, and since this is only an approximation, therefore this block diagram is approximately equal to this block diagram. We have talked about this step in much more details, and we have derived describing functions for different nonlinearities in previous lectures. And the third step is to check whether this assumed solution is the solution to this quasi-linearized system or not. So this third step is equivalent to solving this equation for different values of a and omega. And in today's lecture, we shall talk about this third step in more details, and then we shall apply this describing function analysis approach to certain systems to predict the existence of limit cycles in those systems. So let's talk about this third step, that is how to solve this equation. This equation can be rewritten into this form. Both the equations are the same, written in different ways. We simply bring this to the right hand side and divide both the sides by this describing function to get this expression. That is simple. To solve this equation or this equation, there are two most commonly utilized approaches. There is an analytical approach and there is a graphical approach to solve this equation. Analytical approach, we know that this equation is a complex equation. It can be split into two equations, that is a real part of this equation to be equal to 0 and the imaginary part of this equation to be equal to 0. So here we have split this equation into two parts, and then we solve these two equations analytically for different values of a and omega. This is the first approach, and the second approach is graphical approach. In graphical approach, what we do is that we obtain a graph of this thing and a graph of this thing, and then the intersection of the two graphs, that gives you the solution to this equation. So here the graph of this thing, here variable is omega, so and this thing is a complex quantity, and if we plot it in a complex plane for different values of omega, we get some graph. This you already know, this is basically the polar plot or Nyquist plot of the transfer function, and you can very easily obtain the polar plot and Nyquist plot for a given transfer function. And you also plot this thing on the same graph for different values of a and omega, and the intersection of the two graphs, that gives you the solution to this equation, and this is how we solve this equation. So these are two different commonly used approaches, and let's use these approaches to predict the existence of limit cycles in some systems. We have this system with g of s is given by this transfer function, and we want to predict the existence of limit cycle for two different types of nonlinearities, that is for signum nonlinearity and for saturation nonlinearity with slope k equal to 1. We have talked about both of these nonlinearities in much more details. This is a signum nonlinearity. We have also derived a describing function for this nonlinearity. That describing function is given by this relation. we have derived it in one of our previous lectures. This is saturation nonlinearity. We have also derived a describing function for this nonlinearity that is given by this relation. And we want to predict whether limit cycle will exist in this system for these two nonlinearities or not. Here k is taken to be equal to 1 in this thing. So here was basically 2 multiplied by k, so k is 1. So how to do that? Basically, we need to solve this equation. Which can be split into two equations. That is, a real part of this equation to be equal to 0 and the imaginary part of this equation to be equal to 0. So let's solve it for these two different nonlinearities. Here the transfer function of the system is rewritten, which in terms of j omega is equal to this thing. Simply substitute s equal to j omega to get this relation. Since we want to separate the real part and imaginary part of this complex quantity, so we would rationalize it. This thing, we multiply it by the complex conjugate of this term and complex conjugate of this term. We both multiply it and divide it by this thing. So what do we get in the denominator? In the denominator, j omega appears as it is. So 1 plus j omega, 1 minus j omega, that is 1 minus j square omega square. So square of j is minus 1, so you get 1 plus omega square, and likewise this term multiplied by this term is over here. These terms are also multiplied in the numerator, which can also be written in this form. We have simply taken this j in the numerator, where it becomes minus j, and minus j multiplied by minus j. Here is some mistake. Here should be minus 3, and then this minus j multiplied with this thing. So that is written over here. And imaginary of g of j omega, that is a second part of that particular equation. So this has to be equal to 0. From here, what do we get? What is value of omega? Omega comes out to be equal to square root of 2. Omega is equal to square root of 2. And from the second part of that equation, that is real part of that equation, that is equal to 0. So 1 plus real of this thing is equal to 0. This thing, we know that the nonlinearities, both of nonlinearities are single valued nonlinearities, and therefore this NA of omega, that in both cases is basically function of amplitude only, and that is also real. So we can also take this thing from this outside. So 1 plus NA into real part of g of j omega, that has to be equal to 0. Real of g of j omega can be read from here, and therefore this is 1 plus NA into 3 omega, that is equal to 3 omega divided by this thing, that is equal to 0. Here there was typo, so you need to correct that thing as well. We have substituted omega equal to this thing over here, so we get this relation. This omega cancels out with this omega, and then here omega square is 2 plus 1 is 3, which is written over here, and 2 plus 4 is 6, which is written over here. And then this implies that NA is equal to 6. This is value of NA, and we want to study for two different nonlinearities. What were those nonlinearities? The signum nonlinearity and saturation nonlinearity. So this is the equation, and we want to solve it for A. For signum nonlinearity, this describing function is 4 over pi A, and if we solve it for A, we get A equal to 2 divided by 3 pi. So what is conclusion? We have found the values of a and omega. A comes out to be equal to 2 divided by 3 pi, and omega is square root of 2. That means that there exists a limit cycle in this particular system, and the amplitude of that limit cycle is approximately equal to this thing, and the period of that limit cycle corresponds to approximately omega is equal to square root of 2. So this is the conclusion for signum nonlinearity. And similarly, for the other nonlinearity, which was a saturation nonlinearity, for saturation nonlinearity with k equal to 1, this describing function is given by this relation, and that is equal to 6. So we need to find solution to this equation, and what we observe is that there is no solution to this equation. You cannot find any value of a which will satisfy this equation. No solution means no limit cycle. Why no solution? Why we say that there is no solution to this equation? Because this quantity on the left hand side is always less than or equal to 1. Whatever is the value of a, this quantity will always be less than or equal to 1. So this equation can never be satisfied for any value of a. Hence, no solution exists to this equation, which means that no limit cycle exists in this particular system. So basically, what is value of a? You remember this nonlinearity, saturation nonlinearity, that is given by this graph. Here is saturation nonlinearity. This what was capital A? This capital A. What is this capital A? This is amplitude of the sinusoid. So this A, capital A, is always greater than this small a. Otherwise, this nonlinearity is not effective. Otherwise, that is simply a linear system, and in linear systems, no limit cycle can exist. So this capital A is always greater than small a. What does that mean? If we look at this thing, so this whole thing will always be less than 1. What about this thing? What is the maximum value of this thing? 1. When a, this capital A is equal to a, then that is equal to 1. And what is sine inverse of 1? Pi by 2. Pi by 2, and here is 2 by pi. And in that case, when capital A is equal to small a, this term is equal to 0, and in that case this is equal to 1. In all other cases, it is always less than 1. So therefore no solution exists to this equation for saturation nonlinearity. That means there exists no limit cycle in this particular system. Any other question? We can also solve these equations using graphical technique, as we talked earlier. So for that purpose, here is the MATLAB code. This ZPK command is to enter the transfer function of the system. We have entered the transfer function a. We have taken some values of a. A varies from 0 up to 2 with a step size of 0.1, and then describing function. This is the case for the signum nonlinearity. Describing function is given by this relation 4 divided by pi multiplied by a. Here you observe something different for this product operator. This, if I think it is visible, it is not only steric, but this is also dot steric. What is meaning of this thing? So this, a is not now a scalar, it is a vector. So pi dot multiplied by a means every element of this a is multiplied by pi, and then 4 dot divided by this thing, which means that 4 is you get a vector. This na comes out to be a vector. For each value of a you get a value of this describing function, and na inverse, the inverse of that describing function, that is simply 1 dot divided by na, and we use the plot command to get a plot of this describing function in complex plane. So that is plotted over here. That this straight line is the plot of the describing function for this signum nonlinearity, and on the same graph we plot the Nyquist plot of this transfer function, which is sketched over here. So the two lines, two graphs intersect each other. Here I have simply magnified this region, and we see that the two graphs intersect each other at this point, which corresponds to a frequency of 1.42. That is, limit cycle exists in this particular system. And here is the plot using MATLAB for the second nonlinearity, that is signum nonlinearity. All the steps are the same. Here difference is that a starts from 1 up to 2. Why this value 1? Here it was 0 and here it is 1. Why this value? So this nonlinearity, this saturation nonlinearity becomes effective when this capital A, in that nonlinearity small a is taken to be equal to 1. So when the sign magnitude of the sine wave exceeds 1, only then this nonlinearity becomes effective. Whereas this signum nonlinearity, that becomes effective for any value of a, right? So that is why here a is taken, it starts from 1 up to 2. This is the describing function for saturation nonlinearity. You again notice this division 1 dot divided by a, just to perform element wise divisions and multiplications. And then you can see that there is no intersect between the graph for the this thing and the Nyquist plot. So it means that no solution exists for this particular equation, and hence we expect that no limit cycle will exist in that nonlinear system. Clear? In other example, we again want to predict the existence of limit cycle in this particular system, and the transfer function, this transfer function is given over here, and we want to study the existence of limit cycle for two different nonlinearities, that is for saturation nonlinearity with a equal to 1 and dead zone nonlinearity with the delta equal to 1 and k equal to 0.5. We have already talked about these two nonlinearities, and we have derived describing function for these nonlinearities. Here is a saturation nonlinearity with a equal to 1, and the slope is also equal to 1, I think, not written over here, but slope is also 1, and the describing function for this nonlinearity is written over here. We have derived it in previous lecture. And here is dead zone nonlinearity, and delta is equal to 1, and the slope that is equal to 0.5, and we have also derived describing function for this nonlinearity in our previous lectures. To predict the existence of limit cycle, we need to solve this equation, and that this equation breaks down into two equations, that is real part of this equation equal to 0 and imaginary part of this equation to be equal to 0. So let's solve these two equations for this particular transfer function and these two nonlinearities. The transfer function is written again over here, and g of j omega obtained by substituting s equal to j omega, we get this thing. So j square is -1, and you get this relation. We would like to split into real and imaginary parts. So we rationalize it, multiply this expression with the complex conjugate of this denominator, which is written over here, and then we have this expression. Again, this equation, imaginary of g of j omega equal to 0. Imaginary part is over here. This is imaginary part, so that is equal to 0. What are solutions to this equation? There are two solutions, one omega equal to 0, and the second solution is omega is equal to square root of 8. This solution is trivial solution because oscillations with frequency of 0, that means no oscillations, so we are not interested in this solution. Here is the second solution to this equation, that is omega equal to square root of 8. And then the second part of the equation is the real part of that equation has to be equal to 0, and this can be rewritten in this form: Na taken outside from this relation, because n of a, that is real in both of the cases, for both of the non-linearities. By substituting real of g of j omega over here, real part of g of j omega is read from this expression, and then omega square is equal to 8. We substitute that value of omega over here to get this expression, and then we get Na equal to 0.8. Na is equal to 0.8, and we want to see whether there exists some value of a which satisfies this equation for the two nonlinearities or not. So the same equation written over here, and we would solve it for two different nonlinearities. First nonlinearity is saturation nonlinearity, and if we substitute the expression for saturation nonlinearity over here, this is the expression for saturation nonlinearity, and we want to solve it. We want to solve this equation. So how would you solve this equation? So you remember your knowledge of numerical analysis. Here solving it analytically, that is maybe not easy, and maybe not possible. You can utilize numerical analysis techniques to solve this equation. So how to apply the numerical analysis technique, we talk about it in the next slide. So if we use some technique to solve this equation, a comes out to be equal to 1.455. So what is conclusion? Limit cycle exists in this particular system, and the amplitude of that limit cycle is approximately equal to 1.45, and the frequency or the period of that limit cycle corresponds to omega equal to square root of 8. So that is for saturation nonlinearity. What was the second nonlinearity? The second nonlinearity was a dead zone nonlinearity, and we have derived the describing function for dead zone nonlinearity in our previous lectures. So we substitute here n of a by this relation, and this equal to 0.08, and again we find that there exists no solution to this equation, that is this thing substituted equal to 0.8. There is no solution. Why no solution? Why do you think that there is no solution to this equation? This thing is some negative quantity. This is also this thing negative sign over here. It means that maximum value of the expression inside brackets, that is pi by 2. That is pi by 2. And what is this maximum value of this thing n of a? That is 0.5. Maximum value is when this pi cancels out with this pi, 1 divided by 2 is 0.5. 0.5 is the maximum value of this thing, and that means this expression substituted equal to 0.8, that will have no solution, because this thing is always less than 0.8. No solution means we cannot no solution exists for that particular equation, and that means that there is a high probability that no limit cycle will exist in that particular system with dead zone nonlinearity. So there is still the question that how to solve this equation numerically. You already know numerical techniques. Just to revise your concepts, that is illustrated over here. What is procedure to solve it numerically? Iterations. You write an expression for a. You write an expression for a, and then take an initial guess, and with that initial guess you solve it, you iterate it. So we can rearrange to write it in this form by simply multiplying this term to the right hand side and then bringing this term to the right hand side, and we can further rearrange to write it in this particular form. Bring this whole expression to the right hand side. We have 1 over a, and then a is given by this relation. We have a relation for a in terms of a. We shall take an initial guess of a, substitute it over here, and then get a new value of a. The new value of a will again be substituted into this expression to get another value of a. You will perform these iterations until you converge to some final solution. But remember that this is not the only way to rewrite this equation. The same equation can also be written into this form. For example, bring this term to the right hand side and also this term to the right hand side. We have this expression, and then bring this sine inverse to the right hand side. You have 1 over a equal to sine of this expression, and then what is a? A is 1 divided by whole of this expression. Again you have an expression for a in terms of a. You will take an initial guess of a, substitute it over here, you will get a value of new a, substitute it again, and after some iterations you will converge to some final solution. And you all also know that not this these numerical techniques, these it is not necessary that these will always converge. So when I programmed this thing in MATLAB, it was not converging. Therefore, I have rewritten this expression into another form, and this easily converged in just 2 iterations. Let me write it over here. We take some initial guess for a. Let's take it to be a equal to 2. This is just a guess. I do not know what is solution to that equation, so I have taken a guess, and I write that equation. A is equal to, here a is equal to square root of sqrt square root of 1 minus 1 over a square 1 over a square, and this whole expression divided by 0.4 multiplied by pi minus sine inverse is sine of 1 over a, 1 over a. So I have an initial guess for a, and I have written this relation into MATLAB, and this will give me a new value of a. And then I again substitute this new value of a into this expression, to get another value of a, and I repeat this thing. So you see that this thing is not converging to any value. Each time I get a new value of a. So now I program the second equation. Again, I start with an initial guess of 2 and program this equation. I have programmed this equation into MATLAB. Your calculators can also program this equation, and I get this value of a. I will substitute this value of a into this equation and get another value of a, and then substitute this value again into that expression to get this thing. So what you see is that this solution has converged 1.455 up to 2 decimal points. It is the same, and if I want more accuracy, I can perform another iteration. So 1.4555, so it is converged up to 3 decimal places. So it means that I have found a solution to this equation, this one. So a is equal to 1.455. And you can also solve it graphically using MATLAB. This is code for saturation nonlinearity, the transfer function of the system, and a is taken from 1 up to 10, and then the describing function, inverse of the describing function, and plot of the describing function in the complex plane with a real part on the horizontal axis and imaginary part on the vertical axis. And on the same graph, on the same graph, we plot the Nyquist diagram that is given by this thing, and there is an intersection of the two graphs. That means there exists solution to this equation that we also verified by analytical technique. Here is for the dead zone nonlinearity. Again, everything is the same except that the describing function for dead zone nonlinearity is written over here, and here is the plot for describing function, inverse of describing function, and here is the Nyquist plot. If I zoom this region, you will see that the two curves do not intersect with each other. That means there is no solution to that equation, and which means that no limit cycle exists in that particular system when we have a dead zone nonlinearity.